Welcome to my new calculus channel. My name is John Gabriel. Do not be alarmed by the patch over my right eye. It's there because my right eye hurts. And I normally use the patch so that I can rest it and rather use my left eye with glasses, because without glasses, I can't even see through my left eye. I can't see using my left eye. So, and you may ask, well, how did this come to be? Well, years of software development, 24 years, have brought me to the point where I cannot use my right eye for too long. So, it's just an infirmity I have, but nothing that I cannot overcome. So, now, what am I going to talk to you about today? Well, I'm going to go right back to the very basics in this discussion of the new calculus derivative. It's a very easy concept to understand if you've had a good foundation in geometry. And I'm going to be calling this the new analysis because I'm starting again from the beginning. It's just that so many people have been asking me, well, why is it that you have the derivative equal to k plus q x mn? In other words, what you see here. What you see here is, let me just move this out of the way. Why is it the derivative is actually equal to k plus q x mn? In other words, where q is a function of these three. Well, I'm going to be explaining all this to you in a moment. Let me just get rid of this. Speed up my computer a little bit. Okay, so how do I arrive at this? Well, we'll see why this is true and why it works for every function. Now, what I've done here in this particular demonstration is I've used a simple curve. This is a quadratic curve, which has a very special property. The property that these distances m and n are always equal. And before you get too comfortable, it's not true for most curves, by the way. There is always a relationship between m and n, but it's not an equality, as we see in the case of any quadratic. And this was known, by the way, also by Archimedes. If you read the works of Archimedes and you study his theorems, you'll see that he knew about these properties, okay, long before I did or anybody else did. And so when Isaac Newton started trying to find the slope of a tangent line to a curve, he was just messing about by taking secants like this and saying, oh, well, if I just bring this secant line here, let me just draw a segment here. If I just take this segment line here and I bring it closer, this segment line here starts resembling the tangent line gradient, doesn't it? This particular one here. Just let me put it in red here. So he was fumbling around in the dark. He didn't know what he was doing. Neither did Leibniz. Neither did anyone else before I came along, okay? He was just messing around, saying, okay, well, let's see what happens if I bring these 2 points closer. And that's what he was doing. And he says, oh, it's starting to resemble the slope of this red line, starting to resemble the slope of the tangent line. And that's where he got his flawed definition of the derivative, and which is the one that was handed down to you by the morons, Augustine, Cauchy, and Weierstrass, and all the others who came after him. None of them were able to figure out why calculus works, and none of them knew, just like you don't know why calculus works and why I'm preparing this lesson for you, because Nobody knows these things. Nobody knew these things until I came along. And so you may ask yourself, well, did I invent these things? No, I didn't invent these things, because well-formed concepts are never invented, only discovered. This knowledge, if there are more advanced civilizations than ours, which there probably are somewhere in the universe, they already know all these things. Okay, so well-formed concepts exist independently of the human mind or any other mind. It doesn't even matter if God exists. These concepts would exist. Do you get that? In other words, you cannot refute a well-formed concept. Unlike your bogus calculus, which has limits and epsilonics and all that other bullshit that can be refuted and that I personally have refuted, you cannot refute this knowledge, because this knowledge is what I call noumena, or that's the plural for noumenon. In other words, it's a concept, a well-formed concept or a perfect concept that exists independently of the human mind. That's philosophical, but guess what? That's how you got mathematics, through philosophy, you morons. That's right. If it weren't for Plato, you wouldn't even be looking at this video. Do you get that? My ancestors were brilliant beyond belief. None of you fucking morons or any of your idiotic Neanderthal ancestors who came before me were able to realize these facts. That's why this makes me the great John Gabriel. And I'm not worth only one Abel Prize. I'm worth many Abel Prizes. But that's besides the point, because I'm never going to get any, simply because you're all too fucking stupid. And the people who sit on the Abel Prize Committee, perverted homosexuals and felons like Professor Gilbert Strang from MIT, or Professor Jack Hazinga, a Harvard alumnus, or David Joyce, that the author of that Euclid's Elements site, or any of the other morons who happen to cross my path. They don't have even 10% of my intelligence. Okay? But now I think I've gone off on a tangent a bit. Let me get back to what I was thinking about, what I was talking about. These are well-formed concepts. You cannot rubbish well-formed concepts. Do you understand that? I can rubbish your bogus calculus, but you cannot rubbish the new calculus. And you may think, oh, well, in the new calculus, points of inflection don't have tangent lines. Of course they don't, you morons. The new calculus is well-formed. It's not formed the same way as your bogus calculus. Do you understand that? And one doesn't determine the soundness of well-formed concepts by comparing them with the wrong results formed by orangutans like your ancestors, Newton, Leibniz, and all the others. Does that make sense now? Good. So let's proceed. So really what you're looking at here is very sound geometry. These, if you look at the rise over the run of this tangent line, this is a similar triangle, and it's similar to this triangle, which rests on the endpoints of the secant line that is produced by this function. Look at it, see? Let me just do this, okay? So this is as old as Euclid. Can you see that? And these lengths here are the rise and the run and the extension on both sides, which is shown in the pink. And so how is it that this expression here must always equal to 0? Well, look at it. Because these triangles are similar, in algebra, you're always going to get an expression, unless it's 0, of course. You're always going to get an expression down here because you're dealing with symbols, not numbers. If you have to divide these two out, it turns out that m plus n, by the way, always happens to be a factor of this numerator. And many years ago, I wrote this article called Divisibility Identities. I don't accept that there are real numbers. Real here means any magnitude or distance, okay? And so these following identities are true. And I prove these to you using two kinds of proofs, a proof by mathematical induction and a proof by construction or constructive argument. So the first one by induction is pretty easy because all you dimwits have been taught this proof and you know basically how it works, okay? But I'll also show you in this article, I'll also show you how to prove these things constructively. And I do it here on page 3 without using mathematical induction. I say, notice that this is equal to this expression here, which is a binomial expansion. And I show you a trick, and I proceed to demonstrate how any of these two cases will cover everything, and any function, by the way, because any function can be written down as a binomial. Did you get that? Okay, so in this article, which I don't have time to go through, you can download it and study it on my Google Drive. This was the first time I did this. Now, obviously, this is too complex for a high school student. So what I've done is, on my website, I've shown you how to do this using simple algebra. And I advise you to go there and study how to do it using simple algebra, or look at one of these demonstrations here, this applet, which I show you the definition, and then I give you the proof. Okay, so you can assume that there are innumerably many secant lines, and how to find, how to prove that this is actually the derivative in a very systematic way using steps. Okay, and so when you get to step 3 here, you'll obviously want to come back to this demonstration that I'm giving you now to see why it works. And I've used a simple quadratic. And so what I do is I take the definition. Okay, this is the definition, right? I should have actually placed this definition before this expression here, but we can go from here to here and see how n plus n is always a factor of the numerator. It doesn't matter what expression is up here. Did you get that, moron? It can be a polynomial, it can be a logarithm, it can be any function f with only one proviso. That function must be continuous and smooth. Why? Because it is the tangent line which makes a function continuous and smooth. If that condition is not there, you can take your calculus and shove it up your ass. It's worthless. Calculus only, the methods of calculus only apply to continuous and smooth curves. Well, if it's smooth, it's also continuous. But I say continuous because there are a lot of idiots in mainstream academia, a lot of moronic professors who don't know what the hell they're talking about. So these extensions here that I've marked are actually shown numerically and also algebraically. So if you look at the algebra here, you're going to end up with this expression n minus n, but it gets a lot more complicated than that for any other function, okay? But always this expression will be equal to 0. And it's easy to see from this diagram, yeah? I mean, it doesn't matter what this function is, as long as it's continuous and smooth, there's going to be a tangent line there, and there's going to be a parallel secant line. So it always works. The new calculus is the first and only rigorous formulation of calculus in human history. It's a sound analytic geometry formulation. There is no other. There was no other. There has never been anything like it before I came along. It doesn't matter. I mean, you don't need to listen to those fucking morons like Jean-Pierre Massager, who was constantly bombarding my comments on Sci.Math, or the idiot Dan Christensen from Canada, some university in Canada, a fucking moron who wrote some software on first order logic. I hate those bastards, and I would really wish that they just choke to death, basically. This is how much I hate them. I hate Professor Gilbert Strang from MIT, and I'm just trying to stay alive until he's dead so that I can be happy about that, because that moron caused a lot of damage on Sci.Math, just like Dan Christensen did. So I am full of hatred for these individuals, as I am for most of you morons who claim that I'm a crackpot, and in fact, I'm actually a genius. I hate to say that, but it's a truth. You're all fucking morons, and I'm a genius. Did you get that, morons? Okay. Well, I didn't actually mean to go off on a tangent like that, but I think you need to know your place. You're idiots. Okay, you're idiots. And I don't give a shit if you vote down this video, because it's going to be around long after I'm gone and also after you are gone. And that's the nice part of it. Well, I guess this has gone on a little longer than I intended, but back to my students on Seymour who are willing to learn these facts. I suggest you study these applets, and if you have any questions, please feel free to ask me. Try these things out with different functions, with other polynomials, with logarithms, with trigonometric curves like sine and cos, and you'll see that this works for everything. Okay, it is a sound calculus. It is the only sound calculus. And so I'm kind of tired now, and I'm going to stop. All right. Till next time, I'm John Gabriel, and this is the New Calculus Channel. Goodbye.